Hey up guys, welcome back to another computer science lesson. Today we're going to be looking at ASCII and Unicode. Last lesson we looked at logic gates where we were drawing circuits, looking at equations, looking at truth tables and stuff like that. And the previous lesson we looked at binary. So this all starts to come together now into this module. We're going to be covering Unicode, ASCII and memory today. I know we've covered it before previously this year, but we're going to be going to a GCSE level and ensuring that you understand everything before we move on throughout the module. Okay, so when you press a letter M on a keyboard, it would look like this. So basically there'll be loads of pulses going into the computer of electricity. So when there's not a pulse, it's off. When there is a pulse, it's on, and so on. So it just pushes out. So for an M, it'll be off, on, off, off, on, off, on. So loads of ones and zeros, which are represented by those pulses, as we learned last lesson. And this is called ASCII. So therefore, every character on a keyboard is represented by a binary value. So for instance, the number 7 key, or the I, or the O, or the space, or the enter key. It's all represented by a binary value, and different binary values represent the character or key you're pressing on the keyboard. So uppercase letters have their own different values from lowercase letters. And so we need to come up with a method, well, computer scientists came up with a method in order to represent these various combinations on that keyboard, because you're going to need a different combination for every key that you've pressed. Punctuation symbols even have their own characters as well. So can you please write down these 3 bullet points and also the title representing characters in binary, and then we'll move on to the next one. Okay, so the first thing we're going to look at is ASCII code. Now this was created in the 1960s and it was used for representing the English alphabet. So it's a 7-bit binary value, and the maximum 7-bit binary number you can have is 127. But adding 0, 0, 0, 0, 0, 0, 0, you can have 128 different combinations of these ones and zeros to represent the character. So we were like, oh, great. Okay, so we can do the English alphabet, which is letters A to Z, uppercase and lowercase, which makes 52 possible characters we can have on the keyboard. The space key, the enter key, the full stop, the @ symbol, the comma, the numbers across the top. We can have 128. And we can't go over that because it's 7-bit binary value. And so what happened was they created a table called the ASCII table. I'm going to show you that shortly. But can you please just write ASCII code and then a little dash next to it, and then these bottom 2 bullet points just here. It encodes 128 characters in 7-bit binary codes. Characters include 0 to 9, uppercase and lowercase letters, A to Z, punctuation symbols, and the space character. Okay, welcome back. So here I've got an ASCII table on the screen. Obviously there's more characters, but I wanted to just fit on the letters that we have, and also the space, the comma, and the full stop just here. So as you can see, if I type the letter X on a keyboard in ASCII, it's 88, which would be 0, 1, 0, 1, 1, 0, 0, 0. So that's 88 in binary. So if I tapped the E key on the keyboard, it would be 69, which is 0, 1, 0, 0, 0, 1, 0, 1. And this continues out for every binary number up to 127 plus 0, 0, 0, 0. So I've got a little ASCII game for you guys who may have played it before. Basically, what you need to do is I've got an ASCII code just up here. I would like you to please convert these numbers into letters for me. So you could be asked this in the exam and you could pick up a couple of nice easy marks. They'll give you like the ASCII table and then you just say what it represents. They could give you the binary numbers. They could just give you the numbers, and then you would need to convert them. So let's start off with 76 just up here. 76 represents a capital L. 111 represents a lowercase o. 115 represents a lowercase s. So as a task for you guys, can you please convert this code just here into normal text for me? So pause the video, give it a shot, and then come back. Okay, guys, welcome back. I hope you found that okay. Here is the answer. Lossy compression reduces the file size by losing some quality of the image. So basically, we're going to be covering lossy and lossless compression later on in this module. So I thought it'd be quite fitting to convert it into a code. Okay, so I've got one more challenge, so it's this one. Can you please pause the video and decipher this code and then come back? Thank you. Okay, guys, welcome back. I hope that was okay. So here is the answer. Lossless compression also reduces the file size, full stop. However, comma, this type does not lose image quality. So I've got one more and one final one. I know I said the other one was a previous one, but I'd like to try out with the binary numbers this time. Sometimes it's easier just to convert the binary number into a normal number and then having a look in the table for it. But I'll let you decide. So pause the video, answer that question just there, and then come back. Okay, I hope you found that okay. Here is the answer. It is I am epic, full stop. So well done if you got that. Okay, so now the ASCII code is rubbish because it only represents the English language. What about Greek? What about Mandarin? What about Arabic? There's so many different symbols out there and combinations and letters that 128 just cannot be done. You need to extend it further. You need more combinations to represent loads of other different languages around the world. So to represent these other alphabets for different languages, a new code allowing for more characters is needed. Unicode was developed to use 16 bits, which gives us 65,536 possible combinations, enough to represent every character in every language. So you can have like the umlaut in German, you can have that represented by a different character code. So it could be, I don't know, 507, I don't know if it is. So yeah, the 16-bit Unicode is used around the world today. But there's another problem with this. There's a downside to using Unicode as opposed to ASCII. So can you please write down that middle bullet point just there? Unicode was developed to use 16 bits, giving 65,536 possible combinations and so on. There is a 32-bit Unicode, but it's not really widely used because of the amount of space it takes up. This leads us to disadvantage what Unicode has compared to ASCII. So pause the video, write down the notes, and then come back. Okay, so this is an example of how Unicode is quite prevalent across the world compared to ASCII. So Facebook and Google, you would use Unicode because people speak in different languages on that platform. If you want loads of different languages and areas on your website, for instance, you would use Unicode as opposed to ASCII. So Unicode is mainly used worldwide. Now, there's a big disadvantage to this Unicode. It's 16 bits. So imagine that I was writing a book and it had 10,000 characters. Each character behind that, the way it's stored, and it represents 16 bits. 10,000 times 16 is 16,000 bits. That's quite a lot. Now, if I was writing that text document in, I don't know, ASCII, and it was a 7-bit, and I've got 10,000 characters, it would be 7,000 bits. So therefore, I have just saved a massive amount of space. In computer science, we care about space on our machines so much because we like to make things more efficient. And so you would always like to reduce the amount of space when you send it over the internet. You'll send your file much faster as well. For the email link attachments, you want your file as small as possible, so you can have that fast transmission and fit those email caps. So yeah, ASCII has a massive advantage of that it's a smaller file size. However, you're limited on the amount of characters. Unicode, you have, and are not limited on the amount of characters that you can possibly have. However, you have a bigger file size. What I've just said there, is usually a 4-mark answer in the test. So can you please write in your books? Unicode has a bigger file size, but you can use lots of different characters. ASCII has a smaller file size, however, you're limited just to English character set. So can you pause the video, write down what I've just said, and then come back. Okay, so we're going to be moving on to memory now, and we're going to be looking at the different units of memory we have in computer science. So then you'll be able to convert these file sizes and see how big those file sizes are. So a bit is the smallest form, as we've gone through in the binary module, is either a 1 or it's a 0. A nibble contains 4 bits, and a byte contains 8 bits. Can you write that down? Okay, so this chart just here represents all of the units of memory for computer science, from a byte all the way up to a petabyte. You need to know about the bit, that it's a 1 and 0, and you need to know about the nibble, that it's 4 bits, and you need to know a byte contains 8 bits. Now, this little picture just here really will help you in converting units of memory. So treat it like a ladder. So let's go through it. 1 byte contains 8 bits. 1 kilobyte contains 1,000 bytes. 1 megabyte contains 1,000 kilobytes. 1 gigabyte contains 1,000 megabytes. 1 terabyte contains 1,000 gigabytes. And 1 petabyte contains 1,000 terabytes. Now, it used to be 1,024 each time, but with advertisements and the way people are advertising their products and Windows, it's been changed now to 1,000 each time. So like 1,000 bytes in a kilobyte, as opposed to 1,024, which it used to be. So that 1,024 now is called a kibibyte. So do always say that it's 1,000 and not 1,024. People may correct you, but with modern computer science and the way modern units of memory are done, it's 1,000. So just think 1,000 each time, guys. 1,000 bytes in a kilobyte, 1,000 kilobytes in a megabyte, and so on and so forth. So this helps us with conversion. So these arrows on the left and right, I've got the arrow pointing up, which is times by 1,000, and the arrow pointing down, which is divided by 1,000. So let's say I have 8 gigabytes, and I need to convert 8 gigabytes into megabytes. Well, that arrow to go up the ladder, just here, so I've got my mouse, so we need to go up just here. We need to times that 8 by 1,000, so it will be 8,000 megabytes. Let's say we're converting 8 gigabytes into kilobytes. So we're over here on our ladder, and we times by 1,000 to get to a megabyte, so that's 8,000. And then we times by another 1,000 to get to a kilobyte, that's 8 million. So it's 8 million kilobytes in a gigabyte. Let's go from 9 gigabytes to a byte. So 9 gigabytes, which is here, times by 1,000 goes to 9,000 megabytes, times by another 1,000 goes to 9 million bytes, times by another 1,000 goes to 9 billion bytes. So it's 9 billion bytes in a gigabyte. So literally when you times by 1,000, guys, all you need to do is just put 3 noughts on the end. 3 noughts and 3 noughts. So it's all about the amount of noughts. Okay, so let's try converting 5,000 kilobytes into megabytes. Well, here, this arrow just here says divide by 1,000 when we go down. We're on kilobytes and we need to end up on megabyte. So 5,000 divided by 1,000 makes 5 megabytes. So 5,000 kilobytes is 5 megabytes. Let's say we've got 5 million kilobytes now. So 5 million just here, we need to go to megabyte first. So divide that by 1,000, take 3 noughts off. We now have 5,000 megabytes. And then we need to go one more step to go to the gigabyte. So now 5,000 divided by 1,000 is 5 gigabytes. So therefore, 5 million kilobytes is 5 gigabytes. I hope this helps. Can you please copy this picture down with the arrows as well? You will refer to this so much when you're converting units of memory. Okay, so I've got a worksheet for you now, and what we'll do is you answer the question, then I'll go over the answer. You answer the question, go over the answer, and so on and so forth, as I can't pass you this worksheet. So can you please fill in the blanks just here? It says a bit is either a blank or a blank. and then continue on with the rest. So I'll give you the answer to the first little one. A bit is either a 1 or a 0. All right, so complete the rest and then come back. Okay, welcome back. I hope you found that okay with those blanks. Here are the answers. So a bit contains either a 1 or a 0. A nibble contains 4 bits. A byte contains 8 bits. A kilobyte is abbreviated to KB. Notice that B there is capital. A capital B means byte, a lowercase B means bits. So it contains 1,000 bytes. A megabyte is abbreviated to MB, capitals, and contains 1,000,000 bytes. A gigabyte is abbreviated to GB and contains 1,000,000,000 bytes, so that's 9 zeros. A terabyte is abbreviated to TB and contains that number there. So yeah, it's a huge number. Okay, can you now complete this question for me? It says Reese has purchased a USB memory stick that has a maximum capacity of 8 gigabytes. Reese has 5,000 pictures with each picture taking up 2 megabytes of memory. How many pictures will Reese be able to save on his USB memory stick? Show you're working. So the trick here, guys, is to convert it all to the same unit of memory. Here we've got a capacity of 8 gigabytes, and yeah, a picture represents 2 megabytes. So you could either, so what you could do is you could either convert this 2 into gigabytes, or the easiest way is to convert this 8 gigabytes into megabytes, and then you can divide by 2. And then you'll know how many pictures. All right, so answer that question and then come back. Okay, welcome back. So here's the answer. So we've got 8 gigabytes is equal to 8,000 megabytes. So we've converted it into megabytes. 8,000 divided by 2, he can store 4,000 pictures on that memory stick. Okay, so next question. It says Reese is going to purchase an additional USB memory stick for the remaining photos. What is the minimum size he will need? Show you're working. So don't forget, he's only stored 4,000 photos on this memory stick now. So you need to figure out how much space he needs for that remaining amount of pictures. So figure it out and then come back. Okay, guys, welcome back. So 5,000 pictures to store. He's stored 4,000 on one memory stick, so he's left with 1,000 photos. Now, 1,000 times by 2 megabytes, because we know they're all 2 megabytes each, is equal to 2,000 megabytes. Let's convert that into gigabytes. So we need to divide by 1,000. Therefore, he has to get a memory stick of 2 gigabytes in size. All right, next question. Okay, so I've moved my face cam down a bit so we can answer both questions now. So we've got the hardest one up here where it says Reese also has a USB memory stick with a capacity of 10 gigabytes. He has 3,000 pictures with each photo taking up 10 kilobytes. So you'll need to calculate how much space those 3,000 pictures are taking up. 200 photos with each photo taking up 5 megabytes. So you'll need to calculate how much space those photos are taking up. 10 videos taking up 1.5 gigabytes as a whole. So it's just said we've got 10 videos as 1.5 gigabytes as a whole. You do not need to times 1.5 by 10 here. How much space will be left on Reese's USB memory stick when he has saved everything on it? So he's got 10 gigabytes on this memory stick. How much space will be left? Then can you please answer task 4, which says how many bytes are there in 3 kilobytes, 2.5 megabytes, 2 gigabytes, and then 4 kilobytes. Answer those 2 really tough questions and then come back. Okay, guys, welcome back. I hope you found it okay. I know it was a really, really tough question, so don't worry if you didn't understand it. Now, let's break it down together and we'll go through it. So he has 3,000 pictures of each photo taking up 10 kilobytes. So here we need to do 3,000 times by 10, which would make 30,000 kilobytes. Now, the trick is here to make it all the same units. What we're going to do is we'll put it into all megabytes first, and then we'll convert it into gigabytes later on. So here, 30,000 is equal to 30 megabytes. Now what we need to do is we need to do 200, because it says 200 photos taking up 5 megabytes. So 200 times 5 is 1,000 megabytes. Okay, so now this 1.5 gigabytes, it says 10 videos taking up 1.5 gigabytes as a whole. So we don't need to do anything here other than convert it to megabytes, so we can add it all up. So when we've added, when we add it all up, 30 plus 1,000 plus 1,500 equals 2,530 megabytes. When we convert this into gigabytes, we divide it by 1,000, and it's equal to 2.53 gigabytes. Now, all we need to do is see how much space is left. So we need to do 10 minus 2.53 equals 7.47 gigabytes. If you got that correct, very, very, very well done to you. All right, the next answers for task 4 is 3 kilobytes equals 3,000 bytes, 2.5 megabytes equals 2.5 million bytes, 2 gigabytes equals 2 billion bytes, and 4 kilobytes equals 4,000 bytes. Okay then guys, so that is the end of the lesson today. I hope you found it all okay. Do not forget how to convert ASCII into convert letters into ASCII and Unicode. So literally you look up the table and convert it either into binary, or the number is what it is, and also the other way around as well. Do not forget that ASCII is a very small file size, but limited on the characters available. Unicode is a really big file size, but you have a wider range of characters you can use. And file size is really, really, really important because you want those faster transmission times. So please, please, please do remember that stuff. Don't forget how to convert into different units of memory as well. It's really going to be prevalent in this lossy and lossless compression lesson. So I hope you found it all okay. If there's any questions whatsoever, please do let me know. So I'll see you next week. Thank you. Bye-bye.